Elastic potential energy is 1/2 kx squared. Gravitational potential energy, mgh. Kinetic energy, 1/2 mv squared. Work is the integral of f dot dx. That should be it. The question is straightforward. I would like the maximum compression of the spring. All right. We're done. Bring it to me, please. I'm trying to trick you. I'm going to be successful. Now, first, I have no trouble giving this question to you in this class and expecting you to get the right answer and be disappointed when I don't. I am disappointed. If for no other reason that I didn't even get one person who got the right answer. You see, the right answer is 47 centimeters. Okay? Now, the reason it's not 0.3 is simple. More simple than you probably like to admit, but is simple. So let's get rid of all this stuff here so it's out of the way. Would you guys agree that the block starts with a certain amount of gravitational potential energy? And that after it falls for a certain amount of time, it reaches a point where it has come to rest and the energy is now in the spring. Would you all agree with that statement? So we begin with a certain amount of gravitational potential energy, mgh. And for many of you, that was 9 joules. 2 times 10 times 0.45. 9 joules of energy. You then expertly said, well, I have 9 joules of energy. The spring is now compressed. So the elastic potential energy must equal 9 joules, which is equal to 1/2 kx squared, or 1/2 times 200 x squared. 9 divided by 100, 0.09, square root of 0.09, 0.3, and you get your x equals 0.3. It's not plus or minus. It's 0.3 meters. That's how far the spring is compressed. Plus or minus suggests that you could pull the spring upwards and get the same answer. So anybody put plus or minus, and there was a few, evaluate why you say plus or minus. Some of you tried to walk this through kinetic energy. You didn't have to. We can still compare the two states of the problem. That's fair. In fact, everything about this matches what you did yesterday. But as I said to you, you guys miss details, and you miss them all the time. You don't pay real attention. You pay the kind of attention you're used to in your other classes. And this would have been fine if this was AP Physics 1. But this was question number 1 in 1989, first problem on the exam. I'm going to make this up. There's 4 more questions to come. You see, here's what you did. You decided incorrectly that this was the reference level. The reference level is the lowest point the object obtains. Is this the lowest point the object obtains? No. Gravitational potential energy is an arbitrary reference level, but you have to choose a reference level that makes sense for the problem. If you're going to be comparing two states of the problem, then you better make the reference level the actual lowest place the object obtains. You see, this didn't come up yesterday because it was a slope and the spring was horizontal. And so when the object was compressing the spring, its height never changed. Right? That was yesterday's to set the reference level based on the lowest point the problem obtains. Which means the box starts a distance of 0.45 plus x above the lowest point, where x is how much the spring compresses. So, in fact, I even tried to put, when I put the equation on the board, I put h minus h naught in hopes that you would recognize you don't know the lowest point. This is how much potential energy we have, where x is how much the spring compresses. That has to equal 1/2 k x squared for how much the spring compresses. So I'm going to walk it back. I wasn't trying to trick you. I knew you'd be tricked. And it's not because you're not smart. You did exactly what you saw in the work yesterday, and then you second-guessed yourself because it couldn't be this easy, Mr. Shelton. It wasn't. Go back to the definition. I gave you the definition of potential energy. I was very clear about it, too. And when we talked about gravitational potential energy, how many times did I talk about the reference level? It can't be a little bit. It was a lot. The reference level is the lowest point the object attains in the course of your problem. The green line, not the red line. Did you write yourself a note? You're easy to trick. Here's the thing. This is a quadratic. 2 times 10 is 20, so this is 20 times 0.45 plus x equals 100x squared. And I just divided both sides by 20 and got 0.45 plus x equals 5x squared. And the only reason I'm writing these things out right now is because even now some of you probably will get the wrong answer because you have to solve a quadratic and it doesn't factor. So 5x squared minus x minus 0.45 equals 0. I use the quadratic formula. And you get 2 answers for x. You get a positive answer and a negative answer. One of them makes sense. The negative answer would have been the spring coming up to meet the box. That doesn't make a lot of sense to me. But the other answer is how much the spring is compressed. And it's slightly more than the 0.3 because the box has more energy than what you gave it. Guys follow? If not, this is the problem. This is the thing. Look, yes, fooled me once, Mr. Shelton. Good job. You fooled me. I won't be fooled again. You're going to be. But not this way. I have another way to fool you. Yes?
I have a question just about the x, because you changed h naught for x. Is that okay in any case? Or
I didn't change h naught for x.
is it just
I did not change h naught for x. This would have been h minus h naught.
yeah.
This says that this expression is how high are you above the reference level. So that's anything I want in here that represents my height above the reference level.
Right.
So it's not really changing h naught for x. That's not what I'm doing.
Okay.
I'm saying that this is 0 and I am this high above the reference level. So this h naught is 0. H naught's always going to be what you set to be 0. I put it in there to remind you that you need to figure out what is the baseline for your problem. Where is the lowest point that makes sense for what you're working in the problem?
Right.
Does that make sense?
Yeah.
Okay. So here's what I want you guys to do now, because you're easy to trick. And now with all this lead up, I know you guys are all going to be all uppity about it. It's going to be great. It's going to be great because some of you might get this one, and I like it. So this was question number 2, by the way. So after you were asked to do that, on the exact same exam, you were asked a question that Zach will like. What is the maximum speed attained by the object? They're obtained.
Do we do it on the same paper?
Yeah, no, just do it on new paper. This is notes. I'm not giving you your paper back. I want to grade those. Assign them 50 points and put them into your grades so you can go home and cry. That'll bring me happiness. No, all I wrote. Consider this. You guys keep thinking it's at its maximum speed right when it hits that spring. Well, the moment it touches the spring, how many forces are acting on the box?
2.
That's funny. The moment it touches the spring, it's definitely got weight acting on the box. What's the second one? From the spring?
Spring.
I mean, that's fine. If you remember, though, spring equals minus kx. Right? When it first touches the spring, what's x?
0.
So is there a force in the spring yet? No. That means the net force is downwards, and it's still getting faster. In fact, we'll advance the problem just a little bit further, just a little bit. Let's go right to here. The box has moved a little bit downwards. Why? Because the net force is still downwards. And because the net force is still downwards, the box is going to accelerate downwards, all those rules. Those stupid physics rules that always apply and are always the same. So right now it has moved a little bit downwards. Weight doesn't change, it's still mg, but now the spring is compressed a little bit. What direction's the net force? Still downwards. Is it accelerating? Yeah, still getting faster. It's not getting faster as fast as it was, but it's still getting faster. Which is why it's not 3 meters per second. That is not the fastest it travels, which is what all of you found. That's how fast it's going when it hits the spring. But that's not when it's traveling its fastest. You need to figure out when it stops accelerating downwards. And again, even now, many of you have no idea what that is. But it stops accelerating downwards when the net force is 0. That's when it'll stop accelerating downwards. And then it'll start accelerating upwards and slow down. You need to figure out where that happens. You need to figure out where it's traveling the fastest. Not being mean, just saying it like it is. Again, no new information here, all old information. Right? This is all old stuff. Do it. You can get this one. Now that you know how to do it, this is easy-ish. Now, I don't want to make it hard. You can say Kx equals mg just as good as I can. You did the lab. You know what net force equals 0 looks like for a spring. Okay, I've drawn us another picture here. Right? At this moment, the net force is 0. You think the box is stopped. I know in your heads you do. You say, well, force or balance, it's got to be 0. No, it's moving here. It's been accelerating the whole time. The box can't stop until there's a net force that's upwards on it. This is just the point where it's no longer speeding up. So Kx equals mg, and I'm frustrated that no one can, tell me what this is, but you should. It's not hard. mg is 20, k is 200. This has to be 0.1 meters. Which, by the way, now, again, the thing that I'm worried about, this is the new reference level. This has to be the new reference level. For a problem involving conservation of energy, you need to choose a reference level that makes sense. This is the lowest point in a problem comparing the amount of energy it has when it's dropped and the energy it has at its maximum speed. The reference level is arbitrary. I'm choosing an appropriate reference level for this question as different from the first question. So my box starts here, wherever we had it before. Let me draw a box. There's a box. This is the 0.45. This is the additional amount, 0.1. What kind of energy does it have here? Pretty easy to do this part. But here's where you're going to screw up again. Here's the other trick. If I want to figure out how fast it's going, well, it has gravitational potential energy here. So that's mgh, where h is 0.45 plus 0.1. What do I have to set that equal to? Well, I'm trying to figure out how fast it's going. We know it's got kinetic energy. When it's here, it's moving. When it's here, so that's got to be 1/2 mv squared, sure. But many of you will leave out the fact that the spring is compressed some. Not all of that energy is kinetic. You expected it to be traveling its fastest when all the energy is kinetic. Not in this problem. It's traveling fastest here, but a little bit of the energy has bled off and is in the spring. Right? The spring is compressed 0.1 meters. This one's easier math, though, because you know what x is. X is 0.1. And you know the spring constant. You can figure out how much energy is in the spring. The hard part was figuring this out. They know you're all going to get 3 meters per second. But the actual answer, 3.16 meters per second. It speeds up a little bit past that point. It's going 3 meters per second here, but it's still getting faster. You have some homework questions. correct? There's one I want to speak about now with this question. And if I don't move on, I'm going to be trapped answering the same thing over again. I do not have a spring that I can bring out that we can bounce the box off of. But I have a little spring in the back. I'll let you play with it. You know, drop a little weight on it. Watch it go back and forth, if that'll help. You already played with it once. Maybe you need a new play date. But I'm not saying, you know. Oh, please. No, I want my 2 minutes.
Our ROTC is having a fundraiser this afternoon.
They need it.
Jeremiah's Italian Idols is on campus today, and also
Yeah, they're traveling all over the country. They need it.
the bus ramp after school. The cost is $5 for their frozen treats.
$5 for a little cup of ice?
And posted ROTC program.
All right.
Bus riders, please be respectful and do not bring any food onto the buses.
You're asked to figure out the maximum height of the object after it leaves the ramp. Remember that? If you've seen this one, they tell you how fast it's going here and ask several questions related to that. It reaches a point over here where it's at its maximum height. Be careful. The kinetic energy is not zero there when it's at its maximum height. It still has a sideways velocity. So if you thought you could just set this one equal to a potential energy of, if you thought you could just go potential energy equals kinetic and find out what the height is here, you're wrong. It has kinetic energy there. It's moving sideways. I'm not saying you can't use energy to figure this out. I'm saying you better figure out what component of the velocity is sideways because it still has that at the maximum height. I know I'm asking you to remember stuff from September, and we're having trouble remembering stuff from just before Thanksgiving. But yes, this problem has it. You could just do a projectile problem. You can do, find your two sides here and figure out the maximum height when the y velocity is 0. That's going to be when it's at its maximum height. That works too. Energy will solve the problem, but just don't think that it has no kinetic energy there. Also, a good question asked yesterday, from Zach, by the way, that I think is a reasonable one to talk about here, was you're asked to compare the actual velocity of the object at the ramp with the predicted value, what you would get from conservation of energy if there was no friction. That question is asked. There's no way to find that answer using this or using this. Because the work being done is being done by friction, it relies on knowing the normal force. But the normal force is changing the whole time we're in the loop. There's no easy way to figure that out. Moreover, you never know the length of the track. However, you could compare the actual kinetic energy with the predicted kinetic energy. This is how much kinetic energy you think should be there. This is how much you actually have, which means some energy was lost. The amount of energy lost must be the work done by friction. The energy goes somewhere. That's a good way to compare them. All right, question. All right, we had some kind of slope here. Something like this. Oops. Be more careful. And I put the spring over here someplace. I put the box here, let it slide down the ramp. If this was 0.45 meters, and if this was a 2 kilogram block, and if I say that this is frictionless, and tell you that this is a 200 Newton per meter spring, then yes, the answer would have been 0.3. That's not what happened in this problem.